Croeso nôl, welcome back. Year 11, Physics, Double Science, Work and Energy Booklet, Lesson 3. Please turn to page 16, and at the top of page 16, write down the title, which is Springs. It's Lesson 3, and today's date. A quick overview of what you're going to be learning in this lesson. We'll be learning about the relationship between the force applied to a spring, the extension of the spring, and a constant called the spring constant. We'll be looking at simple systems where springs are connected together, and the effect on the extension and energy stored in a spring. And that'll take us up to page 21. Now, I'll just give you a moment to read that first paragraph. What it says is that whenever you compress, I'll write these words together. So this here is a compression, because you're pushing the spring together. And what you've got here is we're stretching the spring. Whether you compress or stretch, you're now storing energy in that spring or elastic band. Once you take that force away, it returns to its original length. We use springs everyday life, lots of different ways. You can see the photograph at the bottom of the screen, taken from a trampoline. So where you've got a large force, as you would have in a trampoline, you want springs that we call are very stiff, so they don't extend much with a large force. If you can just write down the units, so the unit of force newtons, extension in meters, and the spring constant is newtons per meter. New equation for today then, F equals kx, that's force equals spring constant times extension. And as it says underneath, a stiff spring has a high value of k. Now we're going to complete this table, and in order to complete this table, we're just going to use an animation. Here's an animation where we can change the size of the force. So if I increase the size of the force acting here, if you look up, I'm 56 newtons and so on. And then what you can see is the extension of the spring is changing. If I just take these back to 0 for now, so if I take this back to 0, you can see now the displacement in green, that's what we'll call our extension, is 0. So I can apply different forces, both stretching the spring and compressing the string. And we could also change the spring constant. So if I put in 100 newtons there, I've got an extension of 0.2 meters. If I double the spring constant, I halve the extension, because I'm making the spring stiffer, or more stiff. Okay. Going back to this table, what we're going to do first of all then is mimic a trampoline spring by putting in a spring constant of 500 Newton meters and apply a force of 50 newtons. Then we're going to mimic a ballpoint pen. We're going to apply the same force, but the ballpoint pen will have a spring constancy of 100 Newton meters. Then we can, in here and here, copy down what the extensions are. So let's do the trampoline first. So that's spring constant of 500, force of 50. Spring constant, let's just get that 500 and let's get the force of 50. That's reading 0.10 meters. And in centimeters, that's 10 centimeters. Let's change the spring constant to 100. So take this right down to 100. We've kept the force the same, 50 newtons. And now we've got an extension there of 0.50 meters. So that's an extension of 50 centimeters. Just to summarize that, you can see the two springs, the ballpoint pen spring at the top of the screen now and the trampoline spring at the bottom with the two different extensions. The only difference, of course, is the stiffness of the spring. The force applied is exactly the same. So look at that bottom spring, 50 newtons, extension 10 centimeters or 0.1 meters, with a spring constant of 500 Newton meters. What would happen if we put two springs together, two trampoline springs together of the same stiffness, 500 Newton meters, and we put them in parallel like that, and we applied the same force of 50 newtons? What would happen in terms of the extension? Would it extend the same amount, more or less? I'm going to pause the video and I want you just to think about it and decide on what you think is going to happen. Okay, let's find out. Let's put in 50 newtons. And if we look at the extension now, the extension is 0.05 meters. That's 5 centimeters. So as you probably would have guessed, the extension is halved when you've got the two springs in parallel, because that 50 Newton force is being shared between the two springs. You could almost think of it 25 newtons each. If we did the same thing now and put the two springs in parallel, put those two springs in parallel now, sorry, in series, I should have said. Put those two springs in series. What's going to happen to the extension now? Is it going to be larger or smaller than the original 10 centimeters, or is it going to actually be 10 centimeters? Again, pause the video and decide. So we're going to put that 50 newtons in again now. Let's move it back to 50 newtons. And what you can see is actually we've got twice the extension. The extension is 20 centimeters. So I suppose you could think of that as the 50 newtons is put through both springs. So both springs extend 10 centimeters each. and you add those two extensions together. 10 plus 10 is 20 centimeters, 0.2 meters. Now we're going to look at the energy stored in a spring. Higher tier pupils would need to make calculations on the energy, because the energy stored in a spring is the area under the force extension graph on this particular animation. It's called force displacement. You can see the displacement or extension is what we're going to call it on this graph is 1 meter, and the force applied is 100 newtons. On the left hand side, it shows that the energy stored in the spring here is 50 joules, and if you calculated the area of that triangle underneath the graph, half base times height, half base is 1, so half of 1 is 0.5 times the height is 100, half of 100 is 50 joules. Foundation tier don't need to make those calculations, but you just need to appreciate that the larger the force and extension of the spring, the more energy is stored in the spring. So we can show that quickly here. Okay, so if we just decrease the extension, there's less energy stored in the spring. If we increase the extension, there's more energy. And if that were for a larger spring constant, then you'd need more energy to stretch that spring the same amount. Turn on to page 17, please. This is the investigation for this booklet, where you would measure the extension of a spring by adding different amounts of weight or force to the spring. You plot a graph of force against extension, then calculate the spring constant as it shows underneath, and work done for higher tier. Now to do this then, we're going to watch a video, but as we watch in the video, I want you to record record the extension of the spring for the different forces applied.
Today we're going to be looking at the experiment for Hooke's law. It's a nice simple experiment, really easy to get good data from this one as long as we're careful and precise about the measurements we're taking. So we need to be able to take careful measurements of the length and extension of a spring as we add different amounts of force to cause it to stretch. So hang up the spring, nice and simple. The next thing, in order to make sure that we measure its length accurately, is that we clamp a ruler in place, and specifically we're using a ruler which has no little gap at the end where there's no measurements, but which starts at 0 on the end of the ruler, and we're going to clamp that in place. And I'm going to try and make sure that I've clamped it in place so that the 0 mark is level with the bottom of the spring, and doing it that way means that I'm not going to have to worry about making adjustments from the readings I take off of the ruler to the results that I record in the table, and that resolves one little source of potential errors where I might make a mistake and record something wrong. I'm going to lower the spring just a tad so that the bottom of the coil is level with the top of the ruler, and just check that they're on. Now that I've got them on a level vertically, I want to minimize the difference as much as possible so that while I've still got room to hang the masses off of the spring, I minimize this difference so that I can keep the errors from taking the readings off the ruler as small as possible. So I'm just going to move the ruler forward slightly. Okay, and I think if I get any close forwards, I'm going to be getting in the way of the mass there. Okay, so each of these masses that I'm going to be hanging off it has a mass of 100 grams. Now, when I record my results, I'm not going to be recording the mass in grams, I'm going to be recording the force in newtons, which means we need to convert using the equation F equals mg. 100 grams is 0.1 kilograms. Now, for the sake of this experiment, I'm going to use a value of 10 for G. So each 100 gram mass is exerting a force of 1 newton on the spring. So the forces, nice and simply, that I'm going to have to worry about are 1, 2, 3, 4 and 5 newtons. So that's a nice simple set of independent variables there. Extension, being a distance, is going to be measured in meters. So I'm going to need to make sure that I convert from the centimetre readings on the ruler into meters before I record those into my table. Converting from centimetres into metres, there's 100 centimetres in a metre, so I need to take the measurement in centimetres, divide it by 100. That's my measurement in metres, that's what will go into the table. So, if you've set this up on level with 0 newtons attached, your extension is 0, that is your original length. So all we've got to do now, add the first mass, first weight of 1 newton, and then record, making sure that you get onto eye level, the extension of the spring. Now be careful, these rulers have 2 scales, one counting up on the left and one counting down on the right. Make sure that you are counting off the right scale. So if I make sure that I get onto a level here and take this recording, I have got 35 millimeters or 3.5 centimeters of extension there. Converting that into meters, writing that in meters, I'm going to have 0.035 meters.
Okay, what I'd like you to do now then is just go back to your booklet and record in the extension for each of the different forces. So you can just about make out there the bottom right of the screen. Look, the extension for 1 newton is 0.035 meters, which is 3.5 centimeters. As the experiment goes on, I just want you to record in your table.
Okay, converting that into meters, that is going to be 0.08 meters there. Repeat again, another 100 grams of mass, another 1 newton, stretches a bit further, stop it from oscillating up and down, just a little bit of gentle support to do that. Okay, I'm just going to down that a little bit more. Bottom of the coil now at just over 12.5, I'm going to call that 12.7 centimeters, 0.127 meters. Another 100 grams, so now up to 400 grams or 4 newtons. Make sure it's level again. Okay, come around here. Okay, and the extension now, that looks like 17.3 centimeters. Converting that, divide by 100, that is 0.173. And the last one, for 5 newtons of force. Okay. Just making sure that the spring there isn't catching on the clamp and being supported there, because that would stop the spring from extending as much as it should. But that looks all right. And so for the last one, we've got an extension of 21.9 centimeters. Divide that by 100, and that gives a final extension of 0.219 meters there. So once you've done that, you can
What I'd like you to do now then is make sure that you've got your table in your booklet filled in, so you can see bottom right again, these are your values. Next, what you need to do is use those values recorded on page 17 to plot a graph of force extension on page 18 and then work out the spring constant. But I don't want you to work out the work done until we get to the end of the lesson, because you haven't been, or you won't have been taught how to do that. The spring constant is something you work out by working out the gradient of the graph. So we're going to go back and watch the gentleman in this video show you how to do that. And as he's showing you, you can be plotting your graph.
This experiment then is just to manipulate the data, produce a graph from which we can show the relationship between the force and the extension. Drawing a graph of this data, now usually you would expect to draw the dependent variable on the y-axis. Now this time around, for the purpose of our analysis from these results, we're going to flip that. So we are going to put the force, the independent variable, onto the y-axis. So we have force in newtons on the y-axis and the extension in meters on the x-axis. Okay, so with the axes labelled, the next thing for us to do is to choose a scale. So my largest force is 5 newtons.
Because you're not using a full-size graph paper, you're using this graph here, I've just put down units you could use. Force up to 5 newtons on the y-axis, and then the value here goes up to, that's 25 centimeters or 0.25.
Being equivalent to 1 newton. So I've got 1, 2.
Okay, he's going to show you now how to plot the points. So obviously yours will be slightly different on your graph paper.
First one, at 1 newton, we're going to have an extension of 0.035. So we have 0.01, 0.02, 0.03 and then 0.035.
Okay, I've just fast forward the video. You can see he's plotted his points and he's going to show you now how to draw a line of best fit and to work out the value for K, which is what you will need to do in your booklet.
Just there for the last point. So now we've got our 5 points. We want to draw a line of best fit. Now, even though I know that with 0 newtons of force, we should see the line of best fit going through the origin, lining the ruler up through all of the data points there, we get a much more accurate line of best fit if I let it go just a little bit above. So this intercept here does suggest that taking those results, we may have had a little bit of a systematic error in terms of perhaps where we measured the 0 extension, so having that spring lined up with the top of the ruler properly. So now that we've got the graph drawn, give it a title, and then we're going to need to find the gradient of that line. So, finding the gradient of the line, what we need to do is draw as large a right angled triangle as we can, preferably picking a few points where the line crosses some easy to read values. So, for instance, I'm going to choose...
By the way, for the exam, you won't need to do this, but it's an extension activity to calculate K. You've just got to be able to calculate K from calculations, and not from the gradient of a graph. But it's good practice, especially for higher tier pupils, in terms of being able to calculate the gradient of a graph. So please do so. It will help you with your understanding.
This point just here, between on the 1.5 newtons, and I am going to use the point up at the top for 5 newtons there. I'm going to draw a large right angled triangle. Okay, and now I need to know both the width and height of that right angled triangle there. So if I read down from there and from here, then the extension in meters is going to be 0.22 meters, and over here we have,
you'll have different values on your graph because you'll be taking different points, I'd imagine.
0.055 is going to be equal to 0.165 meters there across. The height of the triangle, doing the same process then on the other axis. Here I've got 1.5.
Now you may want to fast forward the video. You might find this straightforward and just do it yourself. But I'll let the video run because it's good for you to see how to calculate the gradient. It's up to you. Fast forward if you want, or see the whole video.
5 newtons up at the top. We're going across here, and that lines up nicely with the 5 newton mark. So the height of the triangle is the difference between 5 newtons minus 1.5 newtons, gives us a height of 3.5 newtons there. Then lastly, to find the gradient, we're going to divide the height of the triangle. So we're going to do 3.5 newtons divided by 0.165 meters. Put that into the calculator. And that gives a gradient of 21.2 newtons per meter. And that value gives us what is called the spring constant of the spring that we've used for that experiment there. Okay, that value is denoted by the symbol K, which gives us Hooke's law being the relationship of F equals K X, where X is the extension and F is the force applied. Okay, in alternative to using X for the extension, you can occasionally see this symbol replaced with a lowercase e, so that relationship is the same.
We use X, not E. Right, let's go back to the booklet. So you should have now completed that graph, worked out the value for K, the spring constant. You'll be coming back to this graph at the end of the lesson for higher tier pupils. What you need to do now is read through that. You should find that now straightforward, because it just reinforces what you've already learnt. For higher tier pupils only, the last piece of knowledge is to be able to calculate the energy stored in a spring, which is the area underneath a graph, and that's shown here, shaded in blue. So this area here, and remember, if you want to work out the area of a triangle, area, you've learned this in maths, is half times base times height. There's your base, there's your height. And we did look at that quickly earlier on in the video. So the equation you use is this one here, and you can see it's half times f times x, which is the same as half times base times height. So if we look at this question, just read through it first of all, please. This is one for you to do, and higher tier only to do part D. Essentially, it's the same as what you've just done from the previous practical. And 3 and 4 is for you to do. I'll do question 2, which will bring us to the end of the lesson. So question 2, as always, highlight the important parts, which are often the numbers. It says the Bath rugby scrum exerts a force against one of the springs in the scrum machine, causing it to extend by that much. If the spring constant is that much, calculate the force extended on the spring. We use the equation shown above. We've been asked to work on F, so we just remember E0, equation, number, answer units. The value for K, 40,000. Extension, 0.125. And then use your calculator. That's given us a value of 5,000 newtons. Question 3 and 4 is for you to do. And higher tier pupils, please make sure you go back and you calculate the energy stored in this graph. So what you're going to have, I'll just draw a very quick rough idea of what you're going to have. You'll have some points there. You should have drawn in your line of best fit. You would have calculated your value for K by taking 2 points on the graph. Something similar to this, and you'd have divided the change in force, which will be this value, by the change in extension, which is going to be this value. So you'd have done that already, and you'd have answered that here. But the energy stored in the spring is the area under the graph, and the area under the graph is going to be this triangle here. That's the end of the lesson. See you next time. Bye.